Okay, so here we are, the last two videos, and what we're doing today is sort of the culmination of this entire chapter, which is writing electron configurations and orbital diagrams. And there's three rules that really govern how you go about writing these. And the three rules are listed here: the Aufbau principle, the Pauli exclusion principle, and Hund's rule. And I'm going to leave this blank for you to come back to and fill in these rules once we've gone through everything. We've touched a little bit about the Pauli exclusion principle. We'll see that in a little bit more practice in orbital diagrams, and we'll learn today about Hund's rule and in our next video about the Aufbau principle. So looking at this, we're going to start with the simplest atom, and that's hydrogen. Hydrogen has one proton and one electron. How we know how many electrons an atom is, we learned that back in the last chapter. If we know its atomic number, an element's atomic number is the number of protons in its nucleus. And if you have a neutral atom, it will also be the number of electrons. We are just going to focus on the atoms in this chapter, and next chapter we'll look at the electron configuration of ions. So let's take a look. Hydrogen atom has one electron that occupies the 1s orbital. We will always start with the 1s orbital, as that is the lowest energy. So when we write its electron configuration, we write 1s, and then we put a superscript on the orbital shape so that 1 stands for 1 electron. In an orbital diagram, we have boxes or lines that represent each individual orbital, and in order to represent an electron, we use a half arrow. So in the orbital diagram, I just show one electron, one half arrow in the 1s orbital. So how is this going to compare to helium? Well, helium should be very similar, except it will have another electron in it. Its atomic number is 2. Helium has 2 electrons. At energy level 1, there's only one orbital. There's only that 1s orbital. And both electrons go into that 1s orbital. The electrons have opposite spins. And that's what the Pauli exclusion principle was saying. When we look at its electron configuration, it's still the 1s orbital, but now we put a superscript of 2 up top. So now we're saying 2 electrons are in that 1s orbital. And in the orbital diagram, a half arrow up and a half arrow down. That's how we distinguish between the opposite spins of the 2 electrons in the 1s orbital of helium. So we're just going to keep moving on to more complex and more complicated atoms. Next one is lithium. Lithium's atomic number is 3, so it has 3 electrons. At the energy level 1, there's only one orbital, so 2 electrons can go into the 1s orbital. But now we need to put 3 electrons in there. So where does that third electron go? The next electron must go into the next lowest energy level and the lowest energy orbital in that second energy level. And what that is going to be, so 1s2, then 2s1. That's the full electron configuration of lithium. But when writing electron configurations for atoms with multiple levels, we can do this. Scientists abbreviate the configuration using brackets and the element with the filled energy levels. What the heck do we mean by that? Well, elements with filled energy levels, those are the noble gases. The noble gases are all of the elements on the very rightmost column of the periodic table. They all end in On except for helium. So it's helium, then there's neon, argon, krypton, and so on. So we would say in brackets, in this case, the filled energy level 1, representing the inner electrons, we're going to call them core electrons, is symbolized by, and so in brackets, we're writing helium in there because helium is the noble gas that has that 1s2 electron configuration. Its first energy level is completely filled. The valence electrons are the electrons in the outermost energy level of an atom. Lithium has 1 valence electron. That's going to become super important when we start talking about the properties of the element. So it's represented by 2s1. That's its valence electron. So the electron configuration in its long form is 1s2, 2s1. Or I can write in brackets helium 2s1. And in an orbital diagram, 2 electrons go into the 1s orbital, just like helium, and then another electron in the 2s orbital. So for a total of 3 electrons. Let's keep going. Here we have carbon. So carbon has 6. It has 6 electrons. How many of those are valence? Well, if you think about where carbon is on the periodic table, if you look backwards and find the noble gas that's directly behind it, you'll notice it's helium. How many electrons does helium have? 2, which means every electron that carbon has that helium doesn't have, those are valence electrons. So carbon has 4 valence electrons. Another way, we will look at this more next chapter, that you can count the number of valence electrons is the number of tall columns over on the periodic table. If you look at a periodic table to find carbon, how many tall columns over would you go? And it would be 4. The first 4 fill the 1s and the 2s orbitals. The 5th and 6th electrons occupy 2 different p orbitals because of Hund's rule. When you look at the electron configuration of carbon, it actually doesn't, Hund's rule doesn't even matter. We don't even know what it is yet. So it would be the same as helium, and then it would be 2s2. Remember, s can only hold 2 electrons. What gets filled after s orbitals? P orbitals. And it would be 2p. Not 2p6, 2p2. Look at the superscripts. See how there are, if you add up the superscripts, it equals 4. That's the total number of valence electrons. Helium has 2. This is showing where all 6 electrons of carbon are located. Hund's rule, we really don't apply unless we're looking at the orbital diagram. So the lowest energy configuration for an atom is the one where the electrons with parallel spins occupy separate orbitals within that same orbital group. Why? Well, because electrons are negatively charged and they repel each other. So if the electrons have to be in that same sublevel, 2 electrons have to be in the 2p orbitals. Remember, there's a px, there's a py, and the pz. What is the most stable way for those electrons to be? It's not for 2 electrons to be in, let's say, the px. It's for 1 electron to be in the px and 1 electron to be in the py. The handout here says they want to be in separate orbitals, and you see how want is in quotation marks. Electrons are not humans. They can't have wants or needs or desires. They don't like anything. They don't dislike anything. Oftentimes, we will use language like that to make it easier to understand. That's something that we do especially in middle school. Once we get to high school, we want to get away from using language like that because it shows a real lack of understanding as to why this happened. Why do they want to be in separate orbitals? Because they are most stable when they are in separate orbitals. That minimizes the electron-electron repulsion. So I'm just going to change that, or just say, instead of saying want, how about we say are most stable? Okay, the atom is in a lower energy state, another way of saying most stable, if they are in separate orbitals within the same orbital group. So let's see what that means when we do the orbital diagram. First, we fill the 1s orbital, and we always fill a group and then we move on. The 2s we fill and then we move on. Now we have 2 electrons left because remember, carbon has a total of 6. So far we've done 4 arrows, so we need 2 more. What we need to do, and this is Hund's rule, we spread them out. We spread them out in the 2 different 2p orbitals. We're going to see the same thing happen here with nitrogen and oxygen. Nitrogen has 7 electrons, 5 of which are valence. The first 4 occupy the 1s and the 2s orbitals. The 5th, 6th, and 7th occupy 3 different p orbitals because of Hund's rule. So we can say the abbreviated or noble gas electron configuration is helium, then 2s2, 2p3. Right? 2 plus 3 is 5. Nitrogen has 5 valence electrons. Now when we do its orbital diagram, the electrons will fill orbital groups. Then when we get to the 2p orbitals, 1, 2, 3, they spread out. Oxygen's a little bit different because oxygen now has one more electron. It has 8 electrons, 6 valence, which means that when they start to occupy the p orbitals, we can spread out, 1 in each px, py, pz, and then we're going to have to double it up. And remember, when we double them up, they're going to have opposite spins. So same thing, helium, 2s2, 2p, now 4, an electron in the 1s, or 2 electrons in the 1s, 2 electrons in the 2s, 1, 2, 3, 4. It does have one paired electron, one orbital with paired electrons in that p subgroup, p sublevel. Sodium, how is sodium a little bit different? Sodium has 11 electrons. The first 10 electrons. The first 10 electrons fill orbitals 1s and 2s and 2p. The 1s holds 2, the 2s holds 2, the 2p holds 6. 2 plus 2 plus 6 is 10. Those are the inner core electrons, because if you look back, you will see that now neon is the noble gas that comes right before it. And it is the 3s orbital that has 1 electron in it. So 1s2, 2s2, 2p6. And even though I know they're going to be filled up, I still get into the habit of spreading them out, then doubling them up so that I can understand or see how Hund's rule is being applied. Okay, we have the last few here. Beyond 3s and 3p, there are these d orbitals. So we're going to start to fill d orbitals, but not so fast. The 4s orbital is a little bit closer than the 3d orbital. That's maybe counterintuitive. The first number, meaning the energy level, which generally goes with how far it is away from the nucleus, these orbitals are starting to get so close together that things cross over, and the 4s gets filled before the 3d. Okay, so now let's look at potassium. 19 electrons. The first 18 fill those other orbitals, and the last electron fills the 4s, right? If it's 18, find potassium on the periodic table, look back to the noble gas that comes before it. Argon is the noble gas that comes before it, 4s1. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Calcium works the same way. Maybe give calcium a try and then check your work. (4s) is now filled for calcium. And finally, we will see what happens next. Scandium, titanium, and vanadium, these are all transition metals. These transition metals have now the electrons start to go into the d orbitals. So if I look at scandium, scandium has 21 electrons. So it is argon, and then 4s2, 3d1. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Take a second, try titanium and vanadium, and then check your work against my work. Now that we've done some orbital diagrams and some electron configurations, we're going to learn how to do it without sort of this model to fill in and figure out, where are we getting this order? Like, how am I supposed to know that 4s comes before 3d? And are there any other sort of exceptions? Which there are. So that's what our next video will be.